Hello everyone. I'll now talk about harnessing security through runtime reconfigurable transistors. Before that, I'll talk about what exactly these transistors are. So we know that typically in a PMOS or an NMOS configuration, you have a specific current to voltage characterization. For example, there's a PMOS curve, and this is how the NMOS looks like, for example. Now, in reconfigurable FETs, what we can do is to have the same properties of PMOS or NMOS being provided by a single kind of transistor. And we actually observe, it has been observed by the people that silicon nanowire or germanium nanowire or CNT FETs, for example, etc., they actually provide this runtime reconfigurability that you can change from P type to N type or to P type again, depending on what you provide as a control or a program gate over here, right? So here we see an example of the work published in IEEE Electronic Device Letters in 2020, which shows a very thin wire over here, yeah, and it shows that you actually have two kind of gates over here, control gate and the program gate. And depending on the potential applied at the program gate and control gate, you can essentially control the P and N properties of this particular transistor. And it has also been observed in experiments. For example, you get a nice red curve in the P configuration and the N curve in the blue curve in the N configuration. And the two curves are fairly symmetric, actually almost identically symmetric, with very little difference in the on voltage in the two configurations. And the benefits is that such reconfigurability can be readily used to provide bottom-up hardware security. Yeah, because of this reconfigurability, we can actually provide inherent security principles in circuits. Yeah. Um, for example, we are able to have camouflaged layouts, right? Because I will show in my presentation later on how two different circuits can actually have the same kind of layout, and therefore the attacker cannot easily make out whether it's one gate or the other. These layouts also offer robustness to side channel attacks, for example. Yeah, and one of the things I'll talk about now is logical polymorphism. So if you look at the Nand gate, for example, how it is made in a typical CMOS configuration, you have a pull-up network over here and two-gate pull-down network over here. So typically you have PMOS configuration on the top part and an NMOS configuration in the bottom part, right? And you can realize the same thing with an RFET. If you configure the transistors over here as PMOS in the pull-up part and the transistors over here in the NMOS configuration. What you see over here is slightly different version, because now we actually are able to provide two inputs, or rather three inputs in total on the same transistor. And this NMOS can also then have two inputs which can be ANDed together, essentially if they are actually in series over here. So this behaves like a typical NAND gate with the configuration I've explained with the P and the P bar inputs over here. Now what happens is, interestingly, if you change this P to P bar, for example, essentially if you now make the P to ground over here, you will end up with a pull down network in the top part over here and pull up network at the bottom part over here. And this essentially creates now a NOR gate. So with the exact same circuit layout, we are now able to achieve NAND or the NOR configuration depending on the input P or the P bar over here, which configure the appropriate PMOS and NMOS properties of these gates. And actually, mathematically speaking, if you make this as a larger, if P is also an input and this is considered as a higher order function, it becomes like a minority gate, but that's probably beyond this talk. Now, the such logical polymorphism is shown over here. We have discussed the NAND gate, the NOR gate, and the minority gate I mentioned already on the left part over here. In the middle, we have the two input XOR, two input XNOR, or the XOR3, depending on the P input over here. So again, depending on the P value, this exact same layout, exact same circuit can either be an XOR function or an XNOR function. An attacker who only has an access to the layout of this particular circuit is not able to make out whether it's an XOR or an XNOR, and hence he or she is not able to decipher the correct functionality of the circuit. Similarly, over here we have an AOI and the OAI gate functionality, and even AOI, OI, depending if P is an input or not. So one other example of how we can achieve hardware security is in terms of logic locking. If you typically, in the previous presentation, we saw how we can actually use additional gates over here called key gates, and such provides basically a logic lock circuit, because if you have the correct value of K1, K2, and K3, only then the output Y would be correct, otherwise you would get incorrect output. So typically in CMOS configurations, we have to add additional cells over here to provide such logic locking feature. In silicon nanowire, on the other hand, because the XOR itself could either be an XOR or XNOR, depending on the P input, we do not need additional gates. Instead, we can simply encode this particular gate itself as a logic locked gate. And the same thing can be done for NAND and NOR gates, for example, in the circuits as well. And this way, we are essentially able to get a logic lock feature essentially for free in our design. One other property which can be used to achieve security is now structural polymorphism, where we can actually have different designs for the same functionality, right? So in this case, we are showing the examples of 4 different inverters. For example, this is a normal inverter where you have we have programmed the PMOS and NMOS statically. In the other case, we provide a P equal to 0 as an additional input over here, and only when P is equal to 0, this will work as an inverter, as it will basically not be a valid circuit. In this case, P equal to 1, and in the fourth example, P could be either 0 or 1. So in all these 4 circuit layouts, you still get the same inverter configuration, but you have slightly different properties of layouts over here. And these different properties can then be used as a watermarking feature to encode some specific information in the circuit. However, I mentioned about the runtime or the benefits of runtime reconfiguration. The same benefit which we are getting because of the inherent reconfigurability of the transistors could also be a security vulnerability in some cases. And this could happen when there's a misconfiguration of individual or a group of transistors in a circuit. And as a result of this misconfiguration, the pull-up and the pull-down networks could be misconfigured. Yeah. And these are often very hard to identify. Here's an example. Typically in a CMOS circuit, you always have PMOS and NMOS behavior and pull down, PMOS and pull up, right? But in RFET design circuits, because the pull up and pull down is determined by the PMOS and the NMOS configuration at runtime, it could happen that through malicious configuration, intentionally or unintentionally, you may get both the components over here, for example, in a particular configuration, let's say PMOS over here, and when input 1 comes over here, the circuit essentially is entire, both parts are open, right? So in this case, the output over here would be non-deterministic. The same thing happens if you have configured both the transistor and N-type configuration and the input is actually 0. So in this case, you get open circuit, which may not be so bad, but you will get incorrect output. But if you actually configure these circuits in a way that you get a short circuit over here, that's much worse. So here we show the example in case both are PMOS configured and the input of 0 is applied over here. In this case, you get a short circuit behavior from supply to the ground, and likewise in the rightmost figure. So this particular vulnerability has serious problems. First of all, the output over here, which you get for the remaining part of the circuit, is non-deterministic, and therefore this functionality may not be correct. What you also get is actually the short circuit behavior leads to large current through the transistors, which can lead to faster aging of circuits. It can also lead to let's say hardware trojan in the circuit, such that on activating certain keys, certain parts of a circuit in a particular way, the output is not anymore correct. Right? It could also be used to, for example, design a kill switch approach where you can, or a malicious person can trigger a particular circuitry by using some particular keys, which leads to short circuit currents in the circuit, and as a result of that, the circuit essentially fails. So in short, the reconfigurable transistors offer various security measures like logic locking, camouflage layouts, and side channel robustness, etc. However, the same benefit can also lead to serious security vulnerabilities. Thank you very much.